Alright, we're going to do some gas law demos, and you have a sheet for your drawings. You have a stick labeled in this order, PTV, and we're going to do some before and after pictures of what you see done in the demonstrations. So our first demonstration, I have here an empty soda can which has been on a hot plate getting nice and toasty hot. And I'm going to take it, this is the original starting position on the hot plate, nice and hot. And I'm going to take it and I'm going to turn it into that tap water that's in the beaker right there. And there we go. And so here's the after. You can see there's been definitely a change to the soda can in the after position. So now let's talk, I'm going to do one of the drawings with you, this drawing before and after, and then you'll be on your own for the rest of them. So we started off with a soda can, and I know you're going to be awed by my artistic ability. So here's my soda can. And it is open to the air. It's on the hot plate, so I'm just going to write hot, because before it's hot. And there's air inside it and there's air around it. So with air there's pressure. So I'm going to draw some pressure arrows. And the pressure on the outside of the can, since the same air can get inside the can, there's going to be the same amount of pressure. I'm trying to draw arrows the same size, same amount of pressure inside. So this is the before. Okay. Now in the after, it's still my soda can. It looks like it has changed. I'm still going to draw it the same, but here's the big deal. Same pressure outside the soda can, little itty bitty tiny pressure inside. And I know that is true because it like collapsed on itself. Draw some collapsed lines going on here. It kind of got squished. Okay, so that's the before and after drawings, and I want to mark out that this is cold, or at least, you know, compared to the hot side, it's cold. It doesn't have to be cold water. It was room temperature water. Now let's talk about your stick. Now the stick's going to help you know the relationships to fill in these blanks here. And probably the easiest thing to do is figure out what did not change first. One of these three, pressure, temperature, or volume, must stay the same in each of my demos. So what did not change? Well, notice it's the same 12-ounce soda can before and after, so it's volume that does not change. Because volume does not change, I'm going to put as my fulcrum my fingers on my volume. Now what happened to temperature as I went before and after? Well, it went from hot to cold, so temperature is going to decrease. So I move the stick to where temperature decreases. As temperature decreases, what's happening to that pressure on my stick? Notice my stick is telling me as temperature decreases, the pressure is going to decrease. So what I'm marking here, well, as temperature decreased, the pressure must have decreased according to my stick. I kept the volume constant. And do I have evidence that the pressure decreased? Yes, my evidence that the pressure decreased is that my can got all squished up by the higher pressure outside. So we have a relationship in this first example between pressure and temperature, keeping volume constant. Okay, so that's example one. Now I'm going to walk through the other examples. It's up to you to write the before and afters in as I talk to you about them. So be sure you're paying attention and filling those in. And then once you filled in the before and after and watch the demo, you're going to use your PTV stick to know if pressure is constant, how temperature and volume are related. If temperature is constant, how pressure and volume are related. And just like we did, if volume is constant, how temperature and pressure are related. It's a little handy, useful guide you can have for the rest of the chapter as we do our work to ingrain into your mind the way that these variables relate to each other. All right, so this is demonstration number 2. I have a balloon used as a lid on this 2-liter bottle that has only air in it. So there's also air inside the balloon. So this is your before picture. I have a bottle with a balloon on top. The balloon is slightly inflated. This is hot. This is a hot water bath. I've got it soaking in. That's why it's partially inflated there. And the thing about balloons, remember, is the pressure inside equals the pressure outside. They grow and shrink depending on whatever the pressure is to keep the pressure inside equal to the pressure outside. So we know the arrows inside the bottle and the balloon should be equal in size to the arrows you draw on the outside. And of course I want to mark down somewhere that it's hot. That's the before. Now I'm going to take my balloon on the bottle and I'm going to make a change. Okay, and I'm going to change by putting it into a cold water bath. And you can see a change occurring in my balloon. Look at my sad balloon. Okay. And again, remember, balloons change size to keep the pressure inside equal to the pressure outside. So now as you draw it's pulling it down inside the bottle even there. Now as you draw the after, you'll want to mark down this is cold. This is cold water it's in. You used to have a little bit of ice in it, so it's a nice bath. And the pressure arrows inside the bottle are still the same in size as the pressure arrows outside. That's what the balloon does. Balloons keep the pressure inside and outside the same. So now you can tell there's a change in the volume of the balloon. And you'll want to draw the balloon being much, much smaller than it was before. And I'm curious if I got this really cold, if I could really get the balloon to go inside the bottle. You can kind of see it starting to peek in from the outside there. Okay, so by decreasing the temperatures, I've definitely caused a change in the volume of the air inside. Pressure remaining the same. So your pressure is constant because I'm using a balloon, and that's what balloons do, keep pressure constant. All right, that was demonstration 2. All right, here's demonstration number 3. I'm starting initially with a 2-liter bottle full of water with an exception of, it's hard to see, but I have a pipette inside here and it has a weight on the bottom. That's all that is to keep the hole in the pipette facing down. And it might be difficult to see, but there is some air, there's an air pocket in that pipette. Big enough, obviously, that it's going to make it float to the top because it's at the top. So here's the before, my 2-liter bottle full of water with my pipette with some air pocket in it floating at the top. Now here comes my after. I'm going to squeeze the bottle, and as I squeeze the bottle, okay, something's happening to that air pocket. And I'll make it really evident down here. Okay, I'm going to squeeze really hard now. There we go. Did you see it? I'm going to let go a little. Now I'm squeezing a little, letting go a little. Okay. So the after is me squeezing it, and it's down here at the bottom. Okay. So what am I doing by squeezing it? Well, I'm changing the pressure. What's changing inside that pipette that's causing it to float or sink as a side reaction? Well, that is, I'm obviously changing the volume of that air pocket in there. The more I squeeze, the smaller it becomes. So here's your after with the pipette at the bottom, with the air pocket much smaller than it was before, as I am squeezing, putting higher pressure on it. So the pressure arrows need to be rather large. All right. So I'm doing this all at room temperature. Temperature is not changing in my experiment. So we're holding temperature constant. I'm changing the pressure by squeezing it, and we are wondering what's happening. You should have noticed by visual inspection here, should have noticed what happened to the volume of the gas. So you can put your fulcrum here and figure out, as the pressure increased, what happened to the volume. If I let go and the pressure decreases, what happens to the volume. So there you go. That was demonstration number 3. All right, so here's demonstration number 4. I have a 2-liter bottle full of air, and inside I have taped a thermometer, much like you would stick to the outside of a fish aquarium to let you know what the temperature of the water is. And I have one of those nifty Fizz Keeper bottle pumps attached to the top. Now right now I have simply screwed that on so the pressure in the bottle is the same as the pressure outside the bottle. And so you'll want to draw equal arrows in your before picture. And you'll want to note this. Right now, it might be hard to see with the glare. I'm going to try and move this around a bit. Okay. Right now, the temperature colors, you might see a little shade of color here around the 72, 74 area. All right. So this is all the before. We're at like 72 to 74, somewhere in there. And I have the same pressure in the bottle as outside the bottle. Now I'm going to come up here and I'm going to pump. And I'm going to add air into the bottle. And adding air, as we know, adds pressure. And this is oh so much fun, let me tell you. But what you should be able to notice is that the color bands are going to be changing. Do you see how it's turning greenish around 74, saying we're definitely at 74? I'm going to keep pumping and see if we can't get this even higher. It's not as easy to do one-handed. By the way, if I felt the bottle, like I would really notice that there is a significant amount more of pressure in the bottle than before. So I'm going to keep going. Okay, I don't know if you can tell, but there's definitely a color change around 74, and it's starting to change around the 76. We're going to go for like, can we see a definite color change going on? So maybe you can see it's starting to turn light brown around the 76 because I'm getting closer to 76. And again, if I squeeze the bottle, there's a lot more pressure in the bottle than before. And you can see there's definitely a color change happening around the 76 to indicate that I am at 76 degrees in the bottle. I'm curious if I can even get it up to 78. Okay, so anyway, you get the idea. If I kept going, I am actually curious if the pump eventually could like burst the bottle, but that's not something I want to actually be the one trying. So I guess it's one of those questions that will never be answered. But notice the drastic color change now around 76 and starting to change around 78. So here's our after. I have used the pump to add air inside the bottle. So we have more pressure in the bottle than outside, so your pressure arrows inside the bottle should be larger. And I'm still using the same 2-liter volume the whole time, so volume's not changing. But what has changed? We went from the color being down around 72 to now it's very clearly up there at 76. So that's demonstration right there. And you go to your stick, you do your drawings before and after and go to your stick, and if I keep volume the same and I increase pressure, what do I expect to happen to temperature? And you should see that it matches with what your observation is right here. All right, so here's going to be demonstration number 5. What do I have? Well, I have a birthday kind of balloon going on. It's one of those Mylar ones. It is not completely filled. It has lost enough helium that it is not going to float on its own. But now I'm going to, so this is the before, the balloon's on the floor. Okay, it's really not floating. Pressure outside and pressure inside is the same. Volume is what it looks like. I mean, you might kind of draw sort of a squished balloon. Okay, and now I'm going to turn on a lamp, and this lamp is really, going to act like a heat source. That's really the purpose of the lamp. It is a 150 watt bulb in there, which is a size you should never put in a little desk lamp like this, but I have a fire extinguisher handy, so I feel I'm okay. Okay, so as this not totally filled balloon is exposed to the heat, what's going to happen? Well, it can't be a pressure change, because we know balloons change size to equalize the pressure. So regardless of what's going to happen here, the pressure is staying the same. So I am changing the temperature, and I don't know if you can tell, but the amount of squishiness of the balloon is decreasing. It's actually, the volume is getting a little larger. And when I let go, it's getting large enough. Oh, look at that. Now the balloon floats up to the ceiling. So this is the after, the balloon at the ceiling. As I've mentioned, the balloon's a little bit larger than it was before. But I want to show you what's going to happen after you do your after. So it's hanging out at the ceiling, away from the hot lamp. Oh, what's happening? Okay, well, it's not by the hot lamp anymore, so now it's going back to room temperature. And room temperature means cooling. So as it's cooling, the volume is changing. And as the volume changes, it's got less buoyancy. It's more dense. And so it's going to eventually, you can imagine. It would also help if there weren't air currents in the room, but good luck finding a room with no air currents, right? So here we go. Slowly making its way back down. Now, can you predict what's going to happen when it gets back down to the bottom where the heat lamp is there? Yeah, so I really literally could set this up and you could watch it rise and sink over and over again. That is definitely a possibility. But this is what you need for your drawings. The before was when it was down at the bottom, and the after is when it was up at the top. So you go back to your stick. Remember, the pressure stayed the same because balloons inflate and deflate to keep the pressure inside and outside the same. So pressure stays constant. I've changed temperature by putting heat on it. That was the change. What's happened to the volume of the balloon? And then do we have evidence that it enlarged? Yeah, because it floated. All right, that was demonstration number 5. All right, so here's situation 6. And this is most of the setup of the before. So I have a big box with some water, which I've colored green to make it easier to see. I have a jar turned over a candle, and the pennies are just there to be sure the jar doesn't seal against the bottom of the box, that there's a little bit of space for water to move underneath the jar opening. And there is a candle inside. And since all I've done was turn the jar over, that should let you know that the pressure in the jar is the same as the pressure outside the jar. And there is one other addition. So you might want to pause it and draw this much, but then unpause it, because the next part of the before is that the candle's going to be on fire. So part of the before is the candle's on fire, and the point of the candle being on fire is that it's going to be producing heat. We're going to get heat out of the candle. Got heat on my thumb there. Let's try this side. Okay, so there we go. Candle's lit, making heat. And I have the jar. Okay, and the jar is, at the moment, empty. And I'm going to set over the candle, and that's going to be, that moment is going to be the before, where the pressure in the jar is the same as the pressure outside, so the arrows should be the same. And I'm going to lower it now very carefully over the candle. And hopefully you know from experience, hopefully someone showed you somewhere along the way, that the candle's obviously not going to burn forever. And as it starts to slowly die, that's going to change the temperature in the jar. So the before was the candle lit, that's the hot situation. Now that the candle's about extinguished, that means the temperature's decreasing. It's coming back to room temperature. And now this candle's extinguished. And what have you noticed? Can you tell that green water has risen up inside the jar? Okay, so here's the after. The same box, same water, same jar. The candle's now extinguished. So that means this is the cold version, if you will. This is the not hot part of the example. So we've let the temperature decrease. Now I'm using the same jar, so that should mean the volume has stayed constant. So what else has changed along with the temperature? Well, hopefully you've said pressure. So evidenced by the water being pulled up into the jar, we know the pressure in the jar is less than the pressure of the air. So you should be drawing your arrows in the jar smaller than the arrows in the air. And then using your stick to figure out the relationship between pressure, temperature, and volume. And again, volume in this case remained constant. All right, so here's scenario number 7. I have a flask, and I'm going to use a balloon as a lid. And as the balloon was just put on the flask, it's going to act really well as a lid, but that the pressure should be the same outside the flask as inside. I'm going to be using the same flask the whole time, so the volume should be remaining constant. But I want the before to be a situation where we have high temperature. So in order to do that, I'm actually going to put some fire into the flask. So you will want to draw your before situation, including the papers. I have a scrap paper that I am lighting on fire. Trying to get it to spread real fast before I drop it in. Okay, so fire, really hot, hopefully. And then I put the balloon on as a lid. Whew, lots of smoke. So that fire warmed up the air inside the flask. Now we're getting to the after situation where the heated air in the flask is cooling. So as temperature decreases, what's happening to the pressure in the flask? So your stick will tell you, but hopefully also we see some evidence based on what's happening to the balloon. And that's why I used a water balloon. Yeah, you can do this with an egg, but I've always wondered how do you get the egg out of the jar afterwards, unless you like sit there with a long knife cutting it to bits or something. With a water balloon, all I have to do is poke it till it pops, and I get the balloon out. But I want to increase the speed of this final result here. So I'm going to stick it now into ice water. So the ice water continuing the temperature change, the decrease in the temperature, and you can see has a much greater effect on the balloon. And if I gave it enough time to get cold enough, or I had, dry ice or something like that, something even colder, I would certainly get a more dramatic effect. Now this was a very large water balloon to begin with going on here, and now you can see most of it has been pulled into the flask as I increase the temperature. Okay, so you get the idea. You should have been able to draw your after. I'm just trying to go to the extreme to show you what's happening. I want your observations to match what the mathematics say should be happening. And the mathematics say the pressure should be decreasing, and we have evidence of that. The water balloon is being pulled into the flask. Okay, so that was demonstration number 7. 1 to go. All right, here's demonstration number 8. So I have an Erlenmeyer flask with some water and lots of gas in it. And previously I have boiled this water so that it started in a very hot situation. So our before is again a hot situation, at least comparatively to, cold. And so we do have, I capped it after it boiled, so we do have the pressure inside being the same as the pressure outside, and then we're going to use the same volume because the flask is even well stoppered, so it's not going to in any way change volume. So this is the before. You should have some arrows inside and outside your drawing of the Erlenmeyer flask with water with the stopper. You should have some arrows of equal size going on there. And now I'm going to add some ice to the top and hope a lot of it stays up. It's also precarious to put the ice in it and keep it balanced. Wonder if you noticed what happened to the liquid. Oh, there it goes again. And I'm going to hold this so it doesn't knock over. So what's happening? Well, the after is this is a cold situation. The volume's not changing, so as the temperature decreases, what else is changing? Hopefully you said the pressure's decreasing. The pressure's decreasing inside. Draw smaller arrows inside the flask in your after than the outside of the flask. And what are you actually seeing? What's going on with this water? I have been able to decrease the pressure enough that the water's actually boiling inside this flask. And it's boiling at room temperature. This is room temperature boiling water because I've decreased the pressure enough in that flask. Pretty crazy, but that's how they freeze dry things. So that's what's going on there. And be sure you make your before and after, and that should be your 8th one.